Begin. Uh, on Sunday, we talked about the improper integrals over infinite segments. Now, I want to discuss the second type of improper integrals, integrals in which the function is not bounded. But we specify what I actually want to define, and then we'll talk about other problems that can occur when we look at such integrals. So, we discuss improper integrals of the second type. The function is not bounded. So, hello. Formally speaking, let f be a function in the segment from A to B, not including A. It's a round bracket. Um, we say that f is integrable in AB if f is integrable for every um, integrable in the segment from C to B for every C which is greater than A. Of course, we should emphasize that f is a function in AB such that f is unbounded in A to B, but is bounded in C to B for every C to A. Now I'll just write it down. Different sentences. So tachlis speaking, let's write it down in a different color. Choose today. Here. So the problematic point is A. Because of A, the function is not bounded. For example, we can look at 1 above x. Fx is 1 above x in the segment from 0 to 1. In every segment C to 1, when C is a positive number greater than 0, f is bounded, is continuous, whatever you like. But it's the point 0 that makes f unbounded in the segment 0 to 1. So, first of all, formally speaking, f is integrable in such case, in such segment, when it is integrable for every closed segment in the segment itself, just like we did Sunday when we talked about the infinite segments. It is integrable in the segment A to infinity if it is integrable for every segment A to B contained in the segment A to infinity. In this case, we define the integral of f from A to B to be the limit of C when C goes to A of the integral from C to B. Yet again, we define the improper integral as the limit of the proper integral. One can be a bit more precise and say that C goes to A plus, because we're talking about c's that are greater than a. So it goes to a from the right-hand side. It goes to the a plus, and this definition of the integral. Yet again, it's similar to the definition of integral from the first type that we saw in Sunday, but here we are getting closer to the problematic point and not tending to infinity. Let's have an example and then talk about what happens when the problem is on the right side of the segment. For example, let's look at the integral from 0 to 1 of, let's say, I don't know, ln x above x. The problem here is with zero, yeah? The function ln x above x is continuous in the segment from C to 1 for every C greater than 0. So it is integrable. Then by our definition, the integral is the limit of the, yet again, proper integral. Here, c goes to 0 from the plus side. The integral c to 1 of ln x above x dx. Now, as we already mentioned on Sunday, we have two separate questions to answer. First, we answer this question: what is the integral in terms of c? And secondly, what is the limit of what we get in the first question? So how do we calculate the integral? As we know from school, high school, or elementary school, whatever. And we mentioned on lecture number 6 on Newton-Leibniz theorem, we find the antiderivative, and then we plug c in 1. So, yes, ln x, as we mentioned, is continuous. We can use the antiderivative, and that's what we're going to do. And technically speaking, as I mentioned in lecture number 6, what I do is finding the antiderivative, no matter what the boundaries of the integral are, and then we put 1 in c, or whatever the boundaries is, in the second step. So how do I calculate the antiderivative excuse me, an antiderivative of this function? We're seeing ln, we're seeing 1 above x, which is the derivative of ln. So we substitute t as ln x. If t is ln x, then dt is 1 above x dx. So we get the integral of just t. If I look at it correctly, we can write it down more explicitly with like ln x multiplied by 1 above x dx. So it's clearly t dt. And we know what is t dt. T dt is t squared above 2. And getting back to the original variable, we have ln squared x above 2. I don't need the plus c here because we talk about definite integral. So the improper integral, the limit of the proper ones, is the limit of ln squared above 2. No, don't need the integral here. Get down and see more. We need to plug 1 and c. So we have Ln squared of 1 minus ln squared of c. And now, after we finished calculate this integral, we can calculate the limits. It's a simple question. It's not a very tough one. Ln 1 is 0. It doesn't matter. It can be 3 as well, just a constant number. Where do ln c goes when c goes to 0? Minus infinity. So squared with minus, whatever, it's still minus infinity. And we can say that the integral is divergent. Ah, that's it. Oh, 1 into 2. That's a 9. We got to the first trimester of the course. Out of 26, something like that, lectures, we've already in lecture number 9. The integral is divergent. Okay, so that's our definition. Any questions about that? So I want to write down a few notes and then another one, but it's different, so I'll do it separately. Okay, so note. First of all, we can define the improper integral with problem on the right side of the segment. When f is unbounded in the segment with A without B, but is bounded for every or in every. Yeah? Because of the minus here, it is not. Yeah, squared makes it positive, the minus again. But the bottom line stays the same. Everybody's divergent. And start to say, blah, 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 but it's bounded in every segment A to C for C smaller than B, we can say that F is integrable in A to B without B if it is integrable in every segment A to C. I missed the every part. Then we define the integral, the proper one, from A to B as the limit of the proper integrals from A to C, because right now B is the problem, and because C is smaller than B, we tending to B from the left side to B minus. So it's the same definition that from just from the other side. That's one thing I wanted to note. You can do an example, but it's practically the same, so I don't find it very important right now. Second thing, B, I wanted to say, when it comes to the integrals that we saw on Sunday, the first type with infinity, we see the infinity in one of the boundaries of the integral, and we know, okay, it's an improper integral. But right now, identifying an improper integral of the second type can be not very, but sometimes a bit confusing or misleading. Right here, why did I know that this integral is actually improper? The definition of improper integral means that the function inside is unbounded, and because of one of the only because one of the sides of the segment is the problematic one. Here it's zero, the left side. I look at at the denominator and I say, okay, the denominator is zero. When the denominator is zero, the function is probably unbounded because it tends to infinity. It's only partially correct. One can look, let's say, the following integral. From 0 to 1 of sinus x above x dx. Now, the denominator goes to 0 when we are going to 0. So, oh, it's a problematic integral. But on second thought, not at all. Here, even though, that's a right even though, the denominator tends to 0 when x goes to 0, the numerator does that as well. Moreover, we know that the amazing limit, as we mentioned before, the limit of sinus x above x when x tends to 0, specifically when it tends to 0 from the right side, is 1. Meaning that the function of sinus x above x is bounded in 0 to 1. It has 1 in continuity point, 0. So, as we mentioned in lecture number 5, 2 weeks ago, bounded function with finite, and 1 is finite, number of incontinuity points is integrable. The integral is proper. It's not improper. It's integral that calculating it is a whole different question. But saying that it does exist, we know it from lecture number 5. It's not an improper integral. Even though, first look, the denominator tends to 0. And what are we going to do? The denominator goes to 0, then the function is unbounded. No. Function can be not defined at some points, can have incontinuities, and still be integrable in the proper way. If the function is not bounded, and because of the point at the end of the segment, then we're talking about the improper integrals of the second type. Why is it important? Because if I want to use the definition, it's not so bad. I mean, as we mentioned in lecture number 6, the integral as a function, as the area function, is continuous when f is integrable. So the integrals do converges to the integral itself on the whole segment. But if I want to use comparison tests that we're going to show later on later on the lecture, as we already shown for the first type of improper integrals on Sunday, it's not obvious that I can compare proper integrals with improper ones. So when you look at an integral and you think, yes, suspect it is an improper one, just check it for yourself. Don't have to write it down, that the function is actually unbounded, and then you can move forward. If it is not, it's a more simple case. It's a real, a proper integral. Calculating it is something else, but we're talking about definitions. Yeah.
I don't understand why example like when no, does no B have to do with anything that we said no name or not?
I mean, we actually defined, as we did on Sunday when the first type of integrals, we defined two kinds of improper integrals of the second type. One is that the problem is on the left side of the segment. Yeah. And they are basically two separate things.
Yeah. Part B, what? Like I'm not understanding the point. Or,
The point is, the point is that this integral is not improper. If it is, I'm very happy. It is not improper because it is actually a real integral. The fact that it has an incontinuity, the fact that the denominator goes to zero, doesn't necessarily implies that the function is unbounded. Here, the numerator goes to zero as well, and we know the amazing limit sinus x above x goes to one. Unlike ln x ln x above x, when x goes to zero, it goes to minus infinity and then the function is unbounded, and then it is actually an improper integral.
Um, Online proper integral will have a result of infinity.
What do you mean?
Like, uh, so have that only proper integrals of this type, I mean, like one at one point. Oh wait, is it a jump also a possibility?
No, the function should be unbounded.
Should
So
be
it's only a
unbounded.
main singularity.
So okay,
Yeah.
so the result will always be some infinity, right? When you integrate it, because it's unbounded at one of the ends, and on the other end it has to be fixed.
Yes.
So the result will always be positive or negative infinity, no?
No, because even though the area spreads on an infinite segment on the y-axis, it can be convergent, just like in series.
So okay.
Yeah, for example, if instead of a x here, we put
X squared, 1/x squared or something.
yeah, we'll see later on. It's a square root of x. It will work probably. Um, okay, so that's A and B. I had C in mind in the Hebrew lecture at 8 a.m. I had three parts to the note, but I don't remember it right now. So I'll move on as what I said. It's actually it is part of the note, but it's something I want to emphasize, so I'll give it its own title. Let's write it down here. More than one problem. More than a day, one problem. Let's get into details. What we did today and Sunday, we defined four kinds of improper integrals. We defined four types, four kinds, because type is the bigger one, of improper integrals. Let's write them down quickly. One, the integral from a to infinity of f, where f is integrable in every segment a to b. That's what we do Sunday. And on the other hand, we talked about the integrals from minus infinity to a. Let's write it down as well. What is going on? Where or when you like. As integral in every segment from B to A. That's what we talked about Sunday. And on the other hand, what we defined today the integral from a to b of f, where f is not bounded in a to b, but is integrable in every segment C to B, where C is greater than A. Let's write down explicitly. And lastly, the same integral when the problem is in B. So I control C, control V, and change it. It's a segment from A, including A, to B, not including B, integral for every segment A to C, for C that is smaller than B. 3 and 4 we defined today in the first half an hour of the lecture. Now, by definition, we know how to deal with these four kinds of improper integrals. What we don't know how to do, or don't know yet, we don't know how to deal with an integral that has more than one problem in its domain. We talked about it, discussed it on Sunday. What happened when I tried to look at the integral from minus infinity to infinity? And we said that we have to, and the bottom line is by definition, it's very intuitive, but it's a definition nonetheless. We say that we have to split it to two integrals, from minus infinity to something and from something to infinity. And that's exactly what we're going to do here in the general case. If these are, no, say plural, what? Ah, okay, general case. That is four cases are the only cases we know how to deal with.
How much area under delta do you want?
Specifically, the bell curve we know from statistics has a very not nice function.
Oh yeah.
Yes, it's integral. I mean, we cannot find an elementary antiderivative. However, when it comes from minus infinity to infinity, there are ways to calculate it, and it, for the specific parameters, it is one. Yeah. Do you study probability this semester?
Probability, yeah.
Probability. Actually, I don't know how much statistics appear in probability. You probably have a different course for statistic methods or something like that, maybe next semester.
Yeah.
So there, you talk about bell curve, normal distribution, and all the fun connected to it. So what I was trying to say, the focus are the only cases we know how to deal with. So what do we do when the integral contains more than one problem? So the bottom line by definition, as we did with the integral from minus infinity to infinity, lecture number 8, we split the integral to a sum of integrals in which every integral has only one problem from the cases we listed above. Using, let's write it in the brackets, using the additivity of the domain when it comes to integrals. For example, if I want to deal with the integral from minus infinity to infinity of the following function, two numbers that you all like, 6, 7. Better than 69 and 420, right?
That's silver lining for everything.
Yes, there was the hot number meme. Yeah, but now it's 6, 7. If you go through my tests, Infi 2 and Infi 1, you'll sometimes find 69 for 120 or something like that, just for the laughs. Now, if I want to deal with this integral, to how many integrals do I have to split it?
Um,
Think about it for a little. 3, 2, what do you say?
three.
3, 3, 2, 3, 3. Okay. You're all wrong. It's not a big deal. You can try it again next semester. Um, how many problems? I want to split this integral to a sum of these from 1 to 4. Now, of course, we have one problem with minus infinity. Let's choose a number. I don't know, 0. Now, 6 is a problem as well, right? 6 makes the function unbounded. The denominator tends to 0, but numerator is 1. So when you are getting closer and closer to 6, the function goes to infinity or minus infinity. It depends on the side you're looking at. So I can't write something like the integral from 0 to infinity. It contains much problems. I can write down the integral from 0 to 6. And right now, I cannot write down something like the integral from 6 to 7 because it has two problems and we didn't define such integral. What do I have to do is split it as well to integral from 6 to, say, 6.5, yeah, or 6 whatever. And then from 6.5 to 7. And then from 7 to some number, I don't know, 8 is always great. And then from 8, we can go swiftly to infinity without more problems occurring. So, in order to deal with this integral, we have to look at 6 separate integrals. But, as we already mentioned when we discussed the integral from minus infinity to infinity in lecture number 8, when, by definition, the bottom is definition, of course, the integral is additive, but it's definition nonetheless. By definition, the integral converges if and only if all the integrals here converge. In other words, if one of the integrals is divergent, alas, our integral is divergent as well. So now, by definition, this is our definition, I mean, definition, the integral is convergent or converges, verb, if and only if all the integrals in the sum are convergent. Here specifically, the integrals from minus infinity to 0 and from 8 to infinity are convergent because the degree of the polynomial here is 2, as when we said on Sunday, degree is greater than 1, then the integrals of the first type are convergent. But if you look at the other ones, you try to calculate it using definition because we still do not possess any comparison test, you can see that they are divergent. So in this specific case, the integral is divergent because some of the integrals that make him are divergent. Any questions about it? Okay. So yet again, I think I missed something. It's probably not important because I missed it. And here in the first note, uh, leave it be. If I remember it, I'll show it to you, of course. Now, exactly as we did on Sunday, as we did in the first course when it comes to series, we want to talk about the convergence tests. Now, we have only two right now, as we did in Sunday, the comparison test and the limit comparison test. I will explicitly phrase them for the first kind of integrals where the problem is on the left segment, left part of the segment, but one can do it easily by himself and phrase it for the integrals with problem on the right side of the segment. It's basically the same. Don't want to be more boring than I already am. So, um, comparison test or convergence tests. Just as the first type integral, just like first type integral, integral is the first type. We have two convergence tests, comparison and limit comparisons. Next Sunday, inshallah, we will see the Dirichlet convergence test for the first type of integrals. But right now we have two, comparison and limit comparison. No ratio, no D'Alembert, no Ibuya condescending, just this. But as we already know, when we use comparison tests, we need someone to compare with. So who we usually regularly compare with, 1 above n to the power of p or whatever when it comes to series, and the integral of 1 above x to the power of p when it comes to integrals. So first of all, let's start with these integrals, just as we did about the integrals the first step on lecture number 8. Proposition, the integral, write it in separate lines so we can watch it more clearly. The integral from a to b of 1 above x minus a to the power of p converges if and only if. What do you say? What are the proper values of p here?
Isn't it not the same as what we saw on Sunday?
No. On Sunday, which is the same as what we saw in last course about series, it's p greater than 1. Here, it's quite the opposite. It's p smaller than 1. It's not actually the opposite because p equals 1 poles both ways, both sides. In Hebrew, say nofel ben hakisot. I don't know if you an appropriate phrase in English. Doesn't work on both ways. I don't know. יוצא קרח מכאן ומכאן. Hebrew, it's an English problem. Okay. Converges even only if p is more than 1. Let's prove it. By definition, first of all, let's observe, write down formally correctly. We observe that the function is without integral. That's the function itself. Don't need the integral with it. The function itself we can call it fx if you like, is not bounded or unbounded, bounded in the segment from A to B, but it is integrable in the segment from C to B for every C greater than A because it is continuous. The only problematic point is A, and the segment C to B does not contain A, so it's all good because it is continuous. So by definition, we calculate the integral as the limit, just this thing, C goes to A plus of the integral from C to B. And yeah, yet again, as we've already mentioned in lecture number 1, so on, it's probably more convenient to write it as minus p instead of 1 above p, because right now it is easier to see what is the antiderivative. Antiderivative. Just anti. What is the antiderivative of x minus a to the power of minus p? Well, it depends. If p is 1, we get ln. If p is not 1, we get something else. Let's discuss both cases. If p is 1, we have the integral is just ln down. It is ln of x minus a, and we have to put x is c and x is b. So it's the limit of c tends to a plus of ln of b minus a minus ln of c minus a. Fantastic. Ln b minus a is just a constant. We don't look at it. And when c tends to a plus, c minus a tends to 0. Ln of 0 is minus infinity, and minus minus gives us infinity, meaning that the integral is divergent for p equals 1. What do we get? If p is not 1, the antiderivative looks a bit different. If p is not 1, we have, let's write down again. It's all the same. Now the antiderivative is x minus a to the power of minus p plus 1 above minus p plus 1. And we need to plug in x is c and x is b. Now let's do two things. First of all, instead of minus p plus 1, let's write down 1 minus p, okay? And secondly, let's substitute b and c instead of x, where needs b. So we have b minus a to the power of 1 minus p minus c minus a to the power of 1 minus p above 1 minus p. And we don't need these boundaries no more. The question on what is the limit of this expression, probably more correctly, the answer to this question depends on the sign of 1 minus p. If now where c minus a part of 1 minus p goes when c goes to a plus. The base goes to 0. C minus A tends to 0. So what do we know about such an exponential function with base that goes to 0? If the power 1 minus p is greater than 0, meaning 1 is greater than p, we have t minus a, the power of 1 minus p, goes to 0, and the integral converges. On the other hand, if we have 1 minus p is negative, meaning that p is greater than 1, when the base is going to 0 and the power is negative, the whole expression goes to infinity. We have control C and control V dash. It goes to infinity, and integral is divergent or divergent. So for the bottom line, for and only for values of p smaller than 1, the integral converges. Any questions? So let's note um, same goes for integrals with problem in the right hand segment. What do I mean? The integral from a to b of x minus b to the power of b converges if and only if p is smaller than 1. Doesn't mean if it's the right side, the left side causes the problem. The bottom line is the same. It converges even only if p is smaller than 1. Okay. Now we have something to compare with. We can state our comparison tests. So we start with a regular one. Comparison test. Again, I phrase it for integrals with problem on the left end of the segment. It will be the same when you state it for the right end. So this is good to write let f and g be unbounded functions in a to b such that f and g are integrable in every segment C to B for C greater than A. If they are both of the same sign, write down as positive, but negative is the same, just put out -1. If F is greater than 0, but is smaller than G in our big segment from A to B, then the integral of f is smaller than the integral of g. What does that actually means? Meaning that if the intuitively bigger integral converges, then the intuitively smaller integral converges. Let's write it down. Our tachlis, it's a different color. I think we did different color today, or it was in algebra. That's we did the seal color in the beginning. Tachlis, what do we actually know? If the no ig, it's if the bigger one converges, then the smaller one converges. Equivalently, if the it's not if and only if it's the same sentence, just written upside down. If the smaller one diverges, then the intuitively bigger one diverges as well. Okay, and one can think again of the way to phrase it for integrals with problem on the right end of the segment. Basically the same. And practically as well. Let's have an example. But any questions before we discuss an example? Okay. As always, it's good to see an example in order to understand, or at least understand what we do not understand. For example, we look at the integral from 0 to 1. All my examples are 0 to 1, but it's more of the same. Of, let's say, the square root of x squared plus a number you like. Anyone? 5? Okay, 5x. What do you say intuitively? Is this integral divergent or convergent?
Intuitively, I wouldn't say, but it's a convergent, right?
It is. But why is your intuition against it?
I mean, I don't know. It goes to zero, but then you remember that it's like a P of half and it
Nice.
works.
So, take you back in ככה, to the Infi 1 course. If it was a series, okay, let's say we had a series of 1 above the square root of n squared plus 5n, okay? When we do it in series, when we do it in the first type of integrals, what we did on Sunday, we say, okay, what is intuitively the total degree of the fraction? Now it is n squared, but it's a square root. The square root of n squared is just like n. So this, and not talking limit, it's a discussion we do more explicitly when we talk about the limit comparison test, which we'll see in a short time, but we do it here as well. This, let's say, approx, it behaves like 1 above n. Yeah? And we know that the series of 1 above n is divergent, so this series is divergent as well. Now, when we discuss integrals of the second type, we have to think in the same way, but not with the same manners or notions. Meaning that if I look at this integral, I have to ask myself, wait, what actually, who is actually the problem? Who or what is actually causing the function to be unbounded when we are tending to zero? It's not the whole x squared. If I write it down as x multiplied by x plus 5, it's only the x that causes problem. Without the x, even though it's x plus 5, it was a proper integral. And unlike the sinus x above x we've seen earlier, we know how to calculate this integral. It's an immediate one. But when we have here the x, it is not a proper integral, but it's improper integral that behaves like which improper, basic improper integral, the integral with square root of x. Mathematically, algebraically speaking, I give up on the x plus 5, which makes the denominator smaller, which gives us a greater fraction, which gives us a greater integral. Formally speaking, it's not bad. It's very good to write down that the functions, this function and this function are positive in the segment 0 to 1, and 1 above square root of x is greater than 1 above square root of x and x plus 5. Let us have a go a bit and just write down the conclusion. We know that here, talking about the second type of integrals, the integral of 1 above square root x is convergent. The p here, as he said, is half. Square root is like the power of half. And so, now read something. This second, do it the right way. And so, by the comparison test, our integral is convergent as well. The communist integral. So, the way of thinking, the process I run through my mind is basically the same as we did on Sunday, we did on the series in the first course. What from the basic integrals, 1 above x to the power of something, which one of them behaves like my integral? But here, I don't look at the whole power, I just look at what causes the problems. Specifically here, it's x who makes the denominator goes to 0 when we are going to 0. So it's only the square root of x that matters here. Here it worked perfectly fine with the comparison test. Sometimes, as we know, we're going to show that as well, the comparison itself is a bit hard, but limit comparison is easier. And then this kind of thinking is even more important. What do I, from the beginning of the exercise, why do I start to compare it with? Which limit should I calculate? And after we state the limit comparison test, we can talk about examples. Like this. Any questions about the example we did it today? So as I mentioned, I want to show you the limit comparison test, and I want to show you an example for it, and then talk about the connection between integrals of the first type, integrals of the second type. How do I go from one to other? And if we have time, I don't think we're going to have it, but if we have, maybe we'll talk about how to prove one of the comparison tests. But let's not talk big before we finished. We now show the limit comparison test. Yet again, let's copy it from the first one. Unbounded functions, blah, 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 blah. Such that f is on every C and A. Assume that f is smaller. No, don't need that. It's the limit comparison. But we need to assume that they are both do not change their sign through the segment. They are all positive or both always negative. Denote with L the limit of the fraction f above g when x goes to a plus. And now we can say, generally speaking, you want to salute generally speaking, when we use the comparison test, where does x go to? He goes to the problem. When we stated it in Sunday, the problem was infinity, so x tends to infinity. Here, the problem is with a, the point that makes the function unbounded, so x tends to a. Yet again, a plus, because we are coming from inside the segment from c's that are greater than a. We denote this limit by L. A disclaimer, always disclaim it here. L doesn't have to exist. Problem, there are functions, there are series sequences talking about the first course in Phi1, which was very fun. The limit of the fraction not necessarily exists. Minus 1 to the power of n, something like that. But when it does exist, and in the wider concept of convergent, meaning that we can talk about it when it's infinity as well, then we can say something about the behavior of the integrals of f and g. We have three cases. Now this is fourth case, when L does not exist, but we don't talk about it, because then the test is not relevant. First of all, if L is a finite number between 0 and infinity, then the integrals of f and g are what we formally call friends. What is it? Friends. Integral. This one converges if and only if the second one converges. Now, second case, and the third case as well, are less important than the first one and are less useful, but they do exist, so I want to write them down as well. If L is 0, intuitively, it means that the denominator is greater than the numerator because it takes all the fraction to 0. So if the denominator is great, we can say that if the integral of the denominator converges, then the integral of f converges. And the other way around, when the limit is infinity, if L is infinity, let's just control C and control V. If the limit is infinity, then intuitively the numerator is greater than the denominator. In this case, if the integral of the numerator converges, then the integral of the denominator converges. using this logic. Any questions about the test itself? So we already know this type of tests, and we can have an example. We look at, I don't know, integral from, let's say 0 to 1, again. Sinus x or arctangus x? What do you prefer?
You know?
Okay. Sinus x above x, let's say 5 plus a number you like, 21 x power of 3. 3? Nah, let's do it. 3. That's enough. So as we know, as I mentioned before, we have to, before we start to solve, we have to first think our integral, our function, behaves like 1 above x, 1 above x squared, 1 above x to the power of 3 cubed, yeah? And then we can limit compare it to the function we thought of. So how do we do it? First of all, as we've already mentioned, it's important to acknowledge the problem itself and what is just happened to pass by, but it's not actually causing any problem. So if I plug the x squared out, I get this one. Who actually takes the denominator to 0? This is x squared. So on first thought, we should limit compare it to 1 above. What? Yes, but the question is not who has the high power, but who makes the denominator goes to 0. Who makes the integral improper?
Oh,
Yeah, just like, first example with x and x plus 5. So x to the power of 3 is a greater power. I do not disagree. But we yet again talk about the problematic. Who causes the problem? Who makes the denominator goes to 0? It is x squared. So now, on first thought, we should limit compare it to 1 above x squared. Who causes the problem? But on second thought, it's not so simple because we know that sinus x tends to 0 as well. And by our amazing limit, sinus x above x tends to 1, we know that, engineerily speaking, sinus x and x are practically the same, talking about limits when we are going to 0. So right now, on second thought, this function behaves like x above x squared. X because it's sinus in the denominator, and x squared because this was important on the denominator. So we do have x above x squared, which is 1 above x. Let's write it down, but in different color, and then write down the solution itself back in black.
That's not a lot of logical jumps. Just saying, yes, it's similar to x, and then it's similar to x over x squared. Like,
Of course, we have to prove ourselves
okay,
with the limit comparison to observe that the limit is actually a number between 0 and infinity. So, the problem in the denominator is x squared. semicolon. And in the numerator, we think of, no ring, or whatever you pronounce it, we think of sinus x as x, because when we talk about tending to zero, their fraction tends to one, so they are practically the same. So out of the bracket. So our function behaves like x above x squared, which is of course 1 above x. So we will limit compare it with 1 above x. This is the intuition behind our move. I call it the verb is limit compare. We limit compare our integral with integral from 0 to 1 of 1 above x. Yet again, it is not bad, on the contrary, to write down that both functions are positive, so we can use the limit comparison test. It's not so obvious. I mean, sinus x is not always positive, x to the power of 3 is not always positive, so it's should be written down. I want to do other things in our limited time here, so I don't write it down right now. With the integral of 1 above x in 0 to 1, L is the limit of c goes to, or x goes to fs plus. Fs is a 0, is the problematic point here, causes the function to be unbounded. It doesn't matter who we put in the numerator, who we put in the denominator. The bottom line will be the same. I mean, if the limit here is 2, so here it will be half, but 2 and half gives us the same result. The integrals are friends. So it's more convenient. You can do so. The x goes to the denominator. We have this nice little fellow here. One of the x's just cancel each other. Then we are left with sinus x above x. And the rest of the denominator, x cubed plus 21. Now, sinus x above x goes to 1. That was the whole point of choosing 1 above x to limit compare with, as we mentioned in field color. 1 multiplied by, this one is just putting 0 instead of x. It gives us the 1 above 21 as the limit. It doesn't matter if it's 3 or pi or 90 or 121. As long as it's a number between 0 and infinity, we have the same result. L is between 0 and infinity. And the functions, let's write down. Eventually write down 1 above x. And sinus blah, blah, blah. Are positive, or at least non-negative, in x had and integrable in every segment from x not equal to 0, and in every c to 1 for c greater than 0. Yet again, why they're integral? Because this is continuous in these segments. So, by the limit comparison test, our integral of the sinus whatever converges if and only if the integral of 1 above x converges. It does not. So our integral is divergent. Any questions? So, last point I want to discuss here in lecture number 9. It's not a very important one, but let's do it. The connection, how do I swift change from first type integral to second type integral and vice versa? Yes, let's write it down like that. Switching between types of improper integrals. Capitalize the first letters. Um, simply, we just plug, we substitute t is 1 above x. The substitution, let's write that. T is 1 above x. Changes first type improper integral to a second type improper integral, and both vice versa. For example, let's, as simplest example one can have, let's look at this integral. 0 to 1, 1 above x dx. Putting t is 1 above x gives us dt. The derivative of 1 above x is minus 1 above x squared, which by our substitution is minus t squared. So dx is actually minus 1 above t squared dt. But it's not the important point here. The important point I want to show you is how do the boundaries of the integral change. Moreover, or furthermore, why not? Additionally, if t is 1, then if x is 1 in the original integral, then t that is 1 above x is 1 above 1, which is 1 as well. And in the original integral, x goes to 0. One cannot say that x is 0 by definition. It's not an improper integral. X tends to 0. If x tends to 0, and more precisely to 0 plus, then t, which is 1 above x, tends to infinity, because x tends to 0. And so we have that our integral from 0 to 1 of 1 above x becomes the integral from 0 becomes infinity, and 1 becomes 1, stays 1. 1 above x is t, and dx is minus 1 above t squared dt. Let's put the minus in the numerator to look it more there. And here one can change the integral a little bit, but it's not nothing of importance. First of all, t and t squared bite for each one. We are left with t in the denominator. And secondly, we usually look at infinity as the upper bound of the integral. And as we mentioned in lecture number 6 last Sunday, if we change the place of the boundaries, put the lower one as the upper and vice versa, we multiply the integral by -1. So it cancels this -1 here, and we get the integral from 1 to infinity of 1 above t dt. Notice that here the integrand, the function itself, is the same, 1 above x, 1 above t. It's not necessarily always happen, right? What is important that by the substitution of t is 1 above x, 0 becomes infinity, and vice versa. So the integral from 0 to 1, integral of the second type, becomes the integral from 1 to 0 to infinity. Integral of the first type, and generally speaking, that's the sentence today. If the problem is A, if the point A causes the function to be unbounded, then t is 1 above x minus A, will make do the job. We'll change the type of the integral. And if it was integral of 1 above x minus 2 from 2 to 3, so substituting t is 1 above x minus 2 will eventually gives us a first type improper integral. Okay. Let's stop for exit before something happens. Any questions about the enjoyable math we learned today? No. Okay. Very good thing. Next week we continue with improper integrals. Talk about absolute convergence and conditional convergence, just as we did with series. And on Tuesday, we'll talk about the necessary condition from series that the general element goes to 0. It doesn't necessarily happen here, so it's something else. But for next week, just as first of all, finish this week, right? Bye bye.